Thank you.
Hey, good afternoon, everyone, and welcome to the 39th Pacific Institute for the Mathematical Sciences Distinguished Lecture. My name is James McVitie. I'm an assistant professor in the Department of Math and Stats and one of the organizers of the PIMS Distinguished Lectures. Before we begin, I'd like to acknowledge that the university is situated on the territories of the Nahiwak, Anishinaabeg, Dakota, Lakota, and Nakota, the homeland of the Métis Nation. The Regina campus is on Treaty 4 land, and the Saskatoon classes are on Treaty 6 lands. It gives me great pleasure today to introduce our PIMS Distinguished Lecturer, Dr. Jiguo Cao. Dr. Cao is Professor of Statistics at Simon Fraser University and conducts research in the areas of functional data analysis, statistical genetics, brain image analysis, and statistical inference for complex dynamical models. Dr. Cao currently holds a Canada Research Chair in Data Science, is the director of the Data Science undergraduate program at Simon Fraser University, and was the recipient of the CRM SSC Prize in Statistics, as well as the BC Sugar Achievement Award. He's published over 100 research articles in statistical methodology and serves as associate editor for the journals of Biometrics, Canadian Journal of Statistics, Journal of Agricultural Biology and Environmental Statistics, Statistics and Probability Letters, and Frontiers in System Biology. Today, Dr. Cao will give a presentation on machine learning for functional data. Please note that this talk is being recorded, so I kindly ask that you hold your questions to the end. Please join me in welcoming our PIMS Distinguished Lecturer, Dr. Jiguo Cao.
Thank you. Thank you. First, I want to thank PIMS to organize this trip. It's a very pleasant arrangement. So I also want to thank the support of PIMS for me to visit Regina. I really like this city. It's it's everything is so close by. Like, so when I go from airport to the hotel, the restaurant, the university, it's also nice to have a lake beside the campus. It's such a beautiful campus. I really like it. Today I'm going to share our recent work. It's about machine learning for functional data. Basically, I will give you a short introduction about the deep learning, and then talk about our recent work called functional neural network, and then show you some results. My research area is called functional data analysis. This is kind of a growing research area in statistics. Here I want to, functional data is data collected over multiple times, spatial locations, or other continuous at the function curves or images. Here on the screen, I show you, this is the daily temperature in 35 Canadian cities. And so you can see that each temperature over the year can be treated as a function, right? Yes, the one-dimensional function. On the right side is an image of is a brain image. And so you can see here, basically, we can also treat this image as two-dimensional functions, right? And so here, I will write down this data as a function of t here. Okay, so this function can be either one-dimensional or two-dimensional. Yeah, so this is why we call it functional data, because basically, each of our data point is one function. Okay, so traditionally, in statistics, when we look at the data, we look at the data at each time point separately. So the unique feature for this functional data is that we will treat each curve as one single data point. And so by treating this as a function of time, we can have some very nice properties we can use. So we have learned calculus. We know that for a continuous function, we can have the derivative, right? So derivative measure the rate of change of a function. That's kind of something you cannot deal with this easily by look at the discrete observations. The second thing is that when we look at this function as a function of time, we also can treat like how smooth, how continuous the function is, right? So that's another interesting features we use a lot. I will show you later on how we use these kind of features in my following method. Okay. now let me talk about briefly about the deep learning. So many of you have heard about deep learning. Is a hot topic now, and deep learning basically is a traditional neural networks, but now we have more layers and modules, right? So now like you have heard in the news that people have put like 100 million parameters in the neural network, so have a lot of layers and modules. So for this neural network, basically they are nonlinear, hierarchical, and abstract representation of data. It's also they are very flexible, and so they can deal with any input out of the data and also the size of the data as well. So why deep learning are so attractive now? The reason is because now we have a very good algorithm developed. The computation is very fast. We also have a very good computing infrastructure to do the estimation for this over millions of parameters and very quickly. Okay, so this is how the deep learning develop very quickly. And now we also have big data as well, right? So for deep learning, one thing is it requires intensive training. So it requires the sample size for the training data are very, very large. So the more training, basically the neural network tend to be working better. So now, people purposely can collect the data like millions of data points with the labels, and to increase the performance of the neural network. And also we have open source tools like TensorFlow, PyTorch. Okay, so they are very well developed, and for very complicated neural network, you can do the computation of just in less than 10 lines of code. So very easy to use. So just to give you some successful stories, like so AlphaGo is one milestone for the deep learning. And so basically, AlphaGo is a deep learning neural network. So it basically beat the world best Go players. That's never happened before. The second is a generative model. Now generative models are very hot topic. We use the ChatGPTs, right? So here, just so this is one application of generative models. Basically, people can generate a fake faces. Okay, so here, like this face is faked, generated. You can see it's very hard to distinguish the real face and a fake face. Okay. Yes. So this is some application for the neural network. So now let's jump to some math details behind this deep learning. So basically, for deep learning, it will be built based on the artificial neurons. So here, so this will give you one simple example. Suppose we have some input x0 to xn. Okay, so we put some weight w here, and we do the linear combination of this input, and we have this input, and we have one term called intercept in statistics, in the current bias in computer science. So basically, this is a kind of a linear models, right? And we got this z, and so this z is called a pre-activation, and so after doing these linear combinations, they have another nonlinear activation function g here. Okay, so then you can see the final output f will become a nonlinear function of the input x. Okay, so the parameter will be just the weight w and the intercept b here. Okay, so you can see very simple structure, right? So the activation function g is known. It's a very simple form for this activation function. So very simple, but it turns out that these models are very flexible. So the reason is that when they build this network, they were using a lot of these artificial neurons. So here, like for this one, with just one middle layers in a neural network, so we can come with these k neurons, right? In the middle layers, and so basically this middle layer Z will be all be the linear function of the input x, and then we will get this nonlinear activity function project to the function f. Okay, so now we will have a matrix of the weights, and also B is the intercept or bias at the parameters. So this is just the one middle layers of the neural network, and so we can do even more, that we can add the hidden layers inside the neural network. So this H is the hidden layers, and so we can continue and we can project this doing the linear combination of the input x, and then we do the nonlinear activity function g because these hidden layers, and then then we will do the linear combination of these hidden layers, and then we can do another levels of nonlinear projection to the output. Okay, so this is one examples of one hidden layers. Of course, now for many applications, as I showed you before, they using like they may using millions of hidden layers, and therefore the model become very complicated. But the formula actually pretty easy. Okay, so therefore the computation is very fast, but the model are very flexible. Okay, so this is just to give you the ideas about the neural network. Okay, so from so I'm a statistician. From my point of view, about the advantage for the deep learning. Okay, I think the deep learning has two advantages. The first one is the nonlinear approximation. Okay, so when we do this data analysis or the data modeling, the things we want to do is that basically we have the input x1 to xp, and we have output y, right? And so we want to do to learn how this map the function input to the output, the function g here, right? So g generally we believe should be a nonlinear function to make it more flexible, right? And so how to estimate this g function is very complicated. So in statistics, we tried some method like non-parametric estimation method, or some. So generally, it's very hard to deal with estimate this nonlinear function g, because we call the curse of dimensionality, because when the function when we have like multiple input, when we estimate like multi-dimensional functions, it will become very hard to estimate. Okay, so this is the but for deep learning, it seems very natural to do this estimation, nonlinear approximation. So this is the first advantage. The second advantage is that about the interactions. So like when we in statistics, when we learn the linear regressions, interaction is kind of like a big topics when we teach linear regression models. But how to train the model interactions, it seems very complicated. Like we have like AIC, BIC, or doing the all kind of criteria to train the models, to train the interactions. But it's very hard to try all kind of combinations of these interactions. But for the neural network, because they kind of doing this multi linear combinations of this input, so this is naturally to be interactions between these input. Okay, so this is another I find a very nice features for these neural networks. Okay, but when we do so far, when we working with this neural network, you can see here, we assume that the input x actually is a vector, right? So we always assume that the x is x0 to xn minus 1, right? Is a vector, and we do these linear combinations of this vector, right? So this is a kind of one assumption we use for the traditional linear network. So as I said, I'm dealing with a lot of functional data. So the data itself is a function. So this is motivated me, like, because function is different from vectors. So vectors, you don't consider the smoothness over different elements, right? But a function, you naturally want the function to be smooth. Secondly, the vectors, you don't have the order of the vectors. You can exchange the second element with the first element. It's still a good vector, right? But for the functions, you cannot change the first time point with the second time point, right? So therefore, when the input is the functions, they are special. So this is motivating me to think about to design the neural network specifically for the function, for the input at the functions. Okay. So now let me show you how we do this. Okay, so this is one example. So basically, for these examples, we have the basically we have the bike rental data in Washington DC, and so we want to predict the bike number of delay bike rentals using the hourly temperature curves. Okay, so this is kind of show you the 3 days temperatures. So you can see, some days are very pleasant. It's easily, more people will like to rent a bicycle and bicycle around. But some days can be very cold or very hot. And naturally, like, they have less people want to rent the bicycle. Okay, so here, this is our input. And this is a temperature curve. Okay, our output will be the number of rental bicycles. So how can we do these prediction problems? So when this we have this temperature curve, right? So we have this temperature curve at 24 hours. So what we can do traditional neural network is that we have the temperature observed at this 24 hours. So then we will have this measure temperature at this 24 hours as the input. So basically here we will have 24 inputs as a vector, and then we can do this like naturally combinations of this beautifully neural network structure, and we can do the prediction for the number of rental bicycles, right? So this is kind of what if we try the traditional neural network to do it. However, now, as I said, our input is a function. So how can we deal with these functions? So basically, now instead of to treat this the value of the function at this 24 time point separately, I will just treat this function itself as one single input. So now we only have one single input, x of t. Okay, and so our input is xt, and so to deal with these functions, we have to change the weight w and the function as well. So now the weight become a function of time as well, and so then we want to do this weighted average of this curve, right? So naturally when we generalize the vector to the functions, so we will change to the weighted average by using this integral, right? So the weight wt will be just the weight on the integration of xt. Okay, so basically here this integration term can be viewed as the weighted average of the curves, and the weight wt will be estimated separated. Okay, so this is like the how we change the neural network to this functional version. Okay, so after we change this project this xt to a scalar h here, then it will become a scalar, and then we can use the conventional neural network to do the following projection. Okay. So really the special things is how you deal with the first layers. Okay. So how can we estimate these weight functions? So this weight function is naturally a infinite dimensional functions, right? So how can we estimate this function? So we definitely cannot estimate this infinite dimensional function. So what we do is that in functional data analysis, actually we have a very popular trick is that when we estimate these infinite functions, we will express this weight function as a linear combination of the basis functions. Okay, so this is a trick used a lot in functional analysis. Okay, so we're using the basis function to approximate a nonlinear nonlinear functions. So these phi1 to phi l are basis functions, and C1 to CL are the coefficient to the functions. Okay, so basically what we will do is that we will choose the basis functions beforehand. Okay, and then we will this phi1 to phi lt will be given, and then we will estimate the coefficient C by our model. Okay, so this is the ideas. So now C become our parameter. Okay. So generally, mathematicians already give us good tools for the basis functions, and so one popular tool is called cubic B-splines. Okay, so this spline basis functions already shown in mathematics that they have the very good power to approximate any nonlinear functions. Okay, so therefore we will using the cubic B-splines. So how many of you have heard about the cubic B-splines? Can raise your hand if you know about cubic B-splines? Okay, yes, a few. This is not popular in statistics. So let me give you ideas what the cubic B-spline looks like. So this is the cubic B-splines. Okay, so basically here each color represents one cubic B-spline basis functions. Okay, you can see that, for example, this red curve is a bell-shaped curve, right? And so basically this each of these basis functions is piecewise polynomial functions. Okay, so and this each of these functions is only 9 zeros in short intervals. Okay, so in the most part they will just become 0 most regions. Okay, so this is called a compact supported properties for cubic B-splines that will help us to using the sparse computation and to increase the computational efficiency. Okay, so this is a cubic B-splines, and so basically in the computer, if you just tell them, okay, you want to put the location of each of these segments, this is called node in B-splines, and then the computer will generate these basic functions automatically in just one line. Okay. Okay. So this is the first things we can choose in the cubic B-splines to approximate the nonlinear function weight functions. Okay, this is the first thing. The second thing is that when we have these basic functions, they tend to be very flexible, and so basically, you know, they can be can approximate any functions, and we tend to be very vaguely. Okay, so when we estimate these weight functions, we want to control the simplicity of these weight functions. Therefore, we have to control the smoothness on this W of t. So here again, this is the weight function Wt as a linear combination of the basis functions. And so how can we do it? So we know in mathematics, if a function is smooth, means the second derivative of the function should be small, right? So naturally, if you think about if the second derivative of the function to be equal to 0, means the function is a linear function, right? So linear function, generally we think this is the most smooth function ever, right? So therefore, we define this roughly the penalty here by defining this second derivative of the weight functions. Okay, and then we can control this lambda is called a smoothing parameter to control the weights on these roughly the penalty terms, and then we can estimate that this controls this WT by choosing appropriate value for the lambda here. Okay, so this is our special things about the objective functions. We add a roughing penalty here. Yes.
Yeah, so, I'm sorry, is capital L decided ahead of time?
You mean the number of basic functions? Yes.
Okay, so that's like an input?
This is like a user choice. Yeah, we choose based on some
Like maybe the domain or something like that?
depends on generally this L depends on how complex you want your function to be. Okay, so if you want a function to be like a
Function H or?
the function W, the weight function.
System.
Yes, yes.
Okay.
Yeah, okay. Generally we will choose a big numbers for the L. Okay, we will not worry too much about the L. So the reason because even you have a big number of basic functions, by using this roughing penalty, you still be able to control the smoothness on the WT. Okay, so that's the ideas. Then this is just for one input functional covariates. And so, in reality, we can have multiple functional covariates, right? And we can also have scalar covariates as well. And so we can just generalize the formula to be multiple integral term and also the linear combination of these scalar variables as well. Okay, so this is the formula for our first hidden layers. Okay. Yes. So this is the ideas for these schemes of this functional neural network. Basically, we have this K functional input. We have this J scalar inputs, and so for the functional input, we will have functional weights, and for this scalar input, we will have just a regular weight parameters. Okay, and then we can project on this functional input to be some scalar values in the hidden layers, and then we can continue to do the multiple layers in the neural network and to increase the flexibility. Okay. So when we do the training, so basically when we estimate the neural network parameters, we will need to calculate the gradient. Okay, basically it's the derivative of the objective function with back to the parameters. Okay, and so actually it's very easy to do because our weight function is just a linear combination of the basic functions, and you can using the chain rules to do calculate the gradient pretty routinely easily. Okay, and also here we also for our functional neural network, because we don't have using the number of the observed time points as the input. Instead, we will using the whole function as one input. So actually, the number of parameters is decreasing. Okay, so suppose for example, if we have J functional covariates measured at n time points, so the traditionally neural network we will have nj inputs, right? And for our functional neural network, we only have J input, but we also need m basic coefficient to estimate for each J input for the functional weights, right? So therefore, the number parameter will become mj plus 1. Okay, typically the number of basic functions m will be smaller than the number of covariates. Okay, the number of time points. So therefore, our number parameter will be smaller. So this should be there's a mistake here. It should be m less than n. Okay. Yes, the number of function will be less than the number of time points. Okay. Another advantage for this functional neural network is that we have better interpretations. So for the conventional neural network, like people always criticize, we have like million of these weight parameters. How can we interpret these parameters, right? And but for functional parameters, I will show you now that it's easier because we have these smooth functional weight parameters. So this is just to give you the idea. So this is, I think, for the prediction problem for the bicycle rental problems. So basically, we are doing the training, and so this epoch it basically is the iteration. Okay, so every time we do the iterations, the objective function loss function will be keep decreasing, right? And eventually it will like reach to a minimum, and we stop the training. And so this will be our weight parameters for this each of these 24 hours input. Okay, so when you look at these weight values, so how can we interpret these values? So it's very hard to understand, right? What this weight represent? Okay, but if we look at the functional weights, okay, so basically again we will update the weight parameters here, and by minimize this loss function, and so eventually you will get these smooth weight functions here, like on the left side. Okay, so you can see here. Basically, for these smooth weight functions, it will have a higher weight between 10 to 20, right? So that's basically it's the peak hours for the range for the bicycles, right? So yeah, so this is kind of naturally can tell you, what's the most important time for the temperature most important, right? For example, at time 15. Is kind of what had the largest weights, and so that's the most influential for the bicycle rentals based on the temperature. Okay, so we get these very smooth weight functions by these reference controls. Okay, we also developed our package called FNN, Functional Neural Network, for general use, and we have designed a five-way functions to use. So now let me show you some results for this functional neural network. So this is the first examples. I also present beforehand as a motivation example. So basically here we want to predict the number of rental bicycles based on the average temperature curves. Okay, so we're choosing 102 days. And so we have their average temperature curves for each day, and also we have their number of rental bicycles. So we have two criteria to measure measure how well the prediction is. So this one is using R squared. So yi hat is the predicted rental bicycles. And Y bar is the average of the rental bicycles over the days. Okay, so this is the first criteria. The second criteria we use is called cross-validated mean square prediction errors. Basically, the smaller of this error, the better, right? Okay. So for the R square, on the other hand, the larger it will be better. Okay. Yes. So for the worst case, if you predict everything to be the average, this will become 1, the R squared becomes 0. Okay. Yes. So this is, we tried the different models as a comparison. So functional neural network is our models. And so we also compare it with the traditional neural network, including convolutional neural networks and conventional feed-forward neural networks. And so you can see our prediction errors tend to be smallest. Our R squared is also the largest. Okay. And this is the standard errors when we do the prediction by try the many times of trimming and test the splits. And so you can see our standard errors are pretty small. Okay. We also tried with other traditional functional regression models. okay, and our performance is also very good. And also we can look at the functional weights, okay. So this is the functional weight we get based on the functional neural networks. And so this is the weight parameters we get for the functional linear models. And so you can see we are just using a much smooth parameters, much smooth functions, and we have a better prediction. The second example is to predict the fat contents of some meat samples. So basically, they have a special absorbance spectroscopy, and so they can measure some kind of fraction of incident radiations absorbed by samples, and they will generate the spectrums of each meat samples. Okay, so this is their spectrum curves, range from 850 to 1050. Okay, so our goal here is that we want to using this spectrum of the meat samples to predict the fat contents of the meat. So our input will be the function as well. Okay, so we also tried different type of neural networks, and also this is functional network is ours, and you can see here our prediction error is the smallest. Okay, compared to other neural networks. The third example is the weather data. So basically here we have the delay average temperature of 35 Canadian cities, and we want to use the temperature curves to predict the annual precipitations of each city. Okay, so so the input is still as functions, and our output is the precipitation amount. So this is the result. And so the last one is the functional network is our models. I can see our prediction error is still the smallest. Yes. Yeah. So the reason is because like at the beginning we think the neural network only works when the sample size is big enough, right? So you see here we only have 35 samples, and actually we are pretty surprised to see that the neural network is still working better than these functional models. Okay, they are more structured models. Okay, we also can get these functional weights for interpretations. We're also doing a simulation study. So here, basically for this simulation study, we have two objectives. So the first one is we want to recover the weight parameters beta. Okay, and the second objective is to try to minimize the prediction. Okay, so in here we generate 300 functional input. Okay, and so we do this we measured our for this estimation of the functional weights, we're using 250 simulations, and for the prediction we're using 100 simulation replicates. Okay, so this is our generally input models. Okay, so this G can be very complicated nonlinear functions, and so this is how we generated the curves x of t, and so this is like how the true function looks like. Okay, so we tried so the first one is just a simple linear function, and the second, the simulation 2 and simulation 3 and simulation 4, they are using some nonlinear functions here. So we just want to see how our model works for both linear relationship and nonlinear relationship. Okay, so we're using this integrated mean square errors to see how well we can recover the functional weight beta here, and so we're using cross validations to choose the smoothing parameter for lambda. Okay, so this is our result for estimated functional weights parameters. FAAN is our functional neural networks. MLM is a functional linear models. Okay, so you can see here for the first scenarios, when the true relationship is linear, definitely linear model will succeed, right? Yes, but for all other nonlinear cases, our models will get a better estimation for the weight parameters. And also in terms of predictions, we have tried some lot of methods, including the least squares, lasso, random forest, gradient boosting, ST boost, projection, pursuit regression. And so we're using this we call it relative mean square prediction errors to see the performance of the models. So basically it will be the mean square prediction errors for each model divided by the minimum of the mean square prediction errors over all models, right? So basically if this one is equal to 1, means that's the best, right? Okay. So this is the result. And so you can see here, so this is the prediction for the simulation 1 and simulation 2. And you can see the FAAN is get the almost covered the 1. So it means that the FAAN are the best models in most simulation replicates. Okay. Same thing for other simulations as well. And so FAAN almost reach the equal to 1 for this relative mean square prediction error. Means FAAN is the beta of the models most times. Okay. So here is my conclusions. So basically we developed the functional neural network to incorporate functional data as input. And so I will show you that in our numerical examples, this functional neural network perform better than many multivariate and functional methods for this longitudinal data. And also our functional weights are easy to interpret. Okay. Yes. So if you want to know more details, you can read our articles, or you can read any questions. You can ask me any questions. Okay. Thank you for attention.